Hello, uh, I am learning discrete Fourier transformation. So while I am doing that, I made a literature review. I didn't see anybody clearly writes the how discrete Fourier transform works. They give the formula and then just they give the picture example they made by the computer comments. Like in Mathematica, it is Fourier, and in square brackets you need to put image data. In MATLAB, FFT, and then in parentheses you are putting your data. For pictures you are writing FFT2 and so on. So for doing that, I made starting documents. So for this case, I started from 1 pixel to real image. That's what I did. They might be wrong because I am learning, so I don't know lots of things. While I am telling you, I will make lots of mistakes. I'm aware of that, so forgive me about that and just try to get what you need. So one important thing is Fourier transform works only grayscale, so pictures are at least for my case it's RGB. I have 3 channels in my image data. I'm gonna just reduce to channel 1, channel 2 and channel 3, and I'm gonna examine separately, and I'm gonna compare the Mathematica code, which is Fourier, to real formula, the function I wrote. So let's start with one dimension. So for one-dimensional case, discrete Fourier transform defined as this, and inverse discrete Fourier transform defined like this. For the 1 pixel, I defined the 1 row and 1 column. This is just creates my output data. It is necessary for that, and this is the first row of it, my output, and dimensions of my picture. In this case I have 1 pixel, and I randomly generate the numbers between 0 to 1 and 3 numbers for 1 pixel, and then I calculate the channels from here. So I make the output and then image. So dimensions, output and image. So let's generate one. So it's running now. So it created this one. This is my input data. So here is the formula. If you see the help of Mathematica, you are gonna see the similar thing. Here is my initial picture data, my input, let's say. So channel 1 to n channel, which is defined here, 3 channel. You can write channel as many as you want, but 3 channel is more realistic, in application wise at least. So after I define the functions, there's a for loop. It calculates the 3 different channels, and it calculates my function, and then this is the appropriate Fourier discrete Fourier transform in Mathematica. So these are creates the images, and then this one choose the right title. So I didn't wrap the texture, so it goes that way. So basically what it does, if it is channel 1, it choose the first one and then it creates this one. If it is channel 2, it creates the channel 2 equals, like, let me show it to you. Like if it is channel 2 equals this, and then it creates this one, and for channel 3 it does same thing, and then print the output. So it is pretty simple. So this is channel 1, this is channel 2, this is channel 3. Important thing is this is by formula and then this is by Mathematica. So also I want to mention Fourier parameters A, B. So 1 and minus 1, they are not default values in Mathematica. I think 1, 0 is the default of the Fourier, and then formula is this. So this is the math for 1 pixel. Okay, let's go to one row of data. So before talking about one-dimensional picture, I want to correct myself. Default Fourier transformation values not 1, 0, they are actually 0, 1. So formula is like this, but when you write this formula you are gonna get a matrix. So you are gonna multiply your image data with this matrix. So that's what I wanted to say. So let's go back to one-dimensional pixel group. Here we enter some row and column, so they are not blue anymore, but they are not also correct. Let's create one more. So here we created 10 pixel, 1 by 10 image. So here is the image data. So for the first pixel we have 0.6 red, 0.2 green, and 0.3 blue for this, and so on. Like this has more green, so pixel 8 has higher green value related to other colors. I don't want to get into code much, because like Mathematica is kinda good software, but also it's expensive. You can write in some free language, so I try to focus on algorithm. Here, two-dimensional. It looks like two-dimensional formula, but actually it is not, because we have one row. Sorry about this, I kind of need help. So we have one row, so 1, 1, this term is only 1, so it cancels other dimension. Also I want to mention, who doesn't have mathematical background, this is summation sign. So in this case it says n, first value of the n is 1, and then last value of n is n call, which is 10 for this case. So we have n column. It's gonna put the values of the n, and it calculates a term and plus it puts the second value, so it increase 1 in every step. So next term will be n equal 2, and it will put to n equal 2, and then it will calculate this term, and then it will calculate the one value of f. So first term will be f0, 0, and then second term will be f01, 02, and so on, and then it will go to second row 1, 0, 1, 1, kinda it will create a matrix. So from that matrix we are gonna create an image. So similar to my function I defined in Fourier transformation, and this is for reduction the data, because you can create RGB values by if you have values between 0 and 1, so it gets rid of the it reduces to 1 degree this value, and this ABS take care of the complex numbers, and then after data is corrected in these two lines, it creates the images, and then this is the same channel 1, channel 2, channel 3. This one just create the outputs, and then it's print comment writes the outputs. Let's look at it. So we run the command. So as you can see, they are same my formula, and actually it's not my formula, function I wrote, and Mathematica function defined. If let me show you what is t data. Let me write let's say you can use the t data. Just I want to show you what does it look like. So I have also, don't forget, this is the channel 3 values for t data. So my first value is 1, which is here. You can't see because it is white, so background color is same. So when you go to 0, when you get closer to 0, you are gonna get the darker color. So this one is darker and this one is darker. So third one and second two from the last. So when this is channel 3, so we have channel same matrix, maybe we can say array, number of arrays, and we are gonna putting them together back. I didn't do it, so I just try to understand the formula of the Fourier transform, discrete Fourier transform. It wasn't necessary for me. If you want, you can put them, and then you can get a colorful picture of this picture's transformation of this picture, if you wish. So I don't know what else I can mention. I think there is nothing else to say about this. Let's go to second dimensional, so we can talk more realistic pictures. In 2-dimension, formula is given here, so it's discrete Fourier transform. Also we talked about in the one row of data, because we had to give it to define 2-dimension, and then we can create the matrix. Even though we don't have more than one row, we have defined a one row. So this is the discrete Fourier transform in 2-dimension, and this is the inverse Fourier transform in 2-dimension. Here I didn't create it until up to 10, and saving space, so basically it does same thing. Only difference I can say, like, first row has 3 columns, so I have 3 pixels for the first row, and then second row has 3 pixels, and third row has 3 pixels. So like here is second row, first column, so second row, first column. So here is the pixels. As you can see from the numbers, this is the green, so green has higher value than others. As before, we just created the initial value for calculation. Everything is same, nothing is changed other than initial value. Also, I didn't mention in the previous case, this ABC stands for absolute, for who doesn't know. Some people could be bored now because I am giving too many details, and they are so simple for anybody in this field. But as I said at the beginning, problem is there is no simple explanation and examples clearly written. That's why I'm doing this video. So here we have the calculation of the by formula, by Mathematica, as before, nothing is changed. So far we calculated from one pixel, one row of pixels, and two dimensional group of pixels. So we can give a neat examples. So one of them is Gaussian matrix and the other one is a real image, so you can see this kind of things everywhere. So let's start with Gaussian matrix. Gaussian matrix is defined in Mathematica as this. So R defines the radius, so R is 7 in our case, so we are gonna create 7 plus 7 plus 1, so which is 0 term, and I'm not gonna enter the data, just we are gonna create the matrix plot. So here it is, and we are gonna check it out because it's two-dimensional, so we can use two-dimensional Fourier transform. So it is already defined as initial, so our initial is Gaussian matrix as a data. So when we run, we get the same value for example, as an example. So here is the real image finally, even though it's not done. So we have the image value, and I reduce its size because it is thousands of pixels, so I reduce this to higher dimension is 30. So we can write it down actually. No, not image data. We can write the dimensions. So when I put the semicolon, which means I don't want to see output of this comment. When I remove it, it will write an output. So I want to see the dimensions of this picture after it's here. Sorry, I don't need to write it down because it's in the output. So resolution is 17 by 30, so it is not real image. As you can see, it's very reduced. Even though I reduced that value, I have to use the parallel computing. It is kinda really huge computational time, I guess, because like I calculated, I think it takes 3 or 4 hours without parallel computation. So I just created the initial value while I am talking and define the function so we can run the simulation. So everything is same except I measure the time because it takes the computational. I wanted to see how long does it take, and parallel table, it comes with the Mathematica. It is very easy to make a parallel computing in Mathematica. You can do without parallel computing, but it will take longer. Nothing will change. It is same as we do two-dimensional transformation. So let's run it. How long does it take to run? While it is running, I can show the parallel computing status. So I have 3 channels, so I'm expecting 3 channels to busy. Yeah, they were busy and they're idle now. So it's done. So it is same as you can see. Maybe you didn't recognize for visualization. We are gonna this is not use appropriate image representation before Fourier transform. This thumbnail wise. In the next section, I'm gonna show the real visualization of it. Just I want to see similarity between my formula and the Fourier transform, so I can understand how Fourier data works, and then I can it is the long calculation continue to my work before, and then so this formula it creates same image writing a Fourier comment. I have questions still here. That's what I was doing. So can notice we can first of all start the image visualization. This is the real visualization of the Fourier
of the image. If you see some white dots, they are probably noise in the picture. When you delete this, what I understand deleting means is writing 0 or something similar to closer value around this value. So as you know, this is a matrix, so it is kind of noise cancellation, and then you can go back to picture and then it will be clear picture. So fast spectrum is shown that way. So my question is, like, I give the initial data, dimensions, and then second channel here, and I don't know why, but I know this is right thing to do. It is just takes the negative opposite sign. It might be negative and then it could be positive after this process. Positive sign off to some values in the D, so which is image data, and then it makes the Fourier transform. So fudge factor is kinda see the better visualization. So if you don't see clear picture, you can change the fudge value, and then absolute value is defined this, so which is magnitude spectrum. As you can see, log value, I believe it is for kind of amplification process doing here. It may not be right, so in the comment below, if you know what this process, if you explain or if you give me a link, so I can read and work on it and I can understand, it will be very beneficial for my case. So with this visualization we finish the our code. If you think there is a big problem in my presentation, please comment below, or suggestion will be greatly appreciated. Thank you for watching my video. Thanks for your time. Have a good one.